Rain, the source of Earth's fresh water and essential to life. Since our earliest ancestors walked the land, rain has shaped humanity and played its part in the rise and fall of civilizations.
There's a famous saying, "We kalani ola kahonua," and in Hawaiian, and it means when the heavens cry, the land lives, and that's what rain is.
And that's why it continues to play a pivotal role in the rituals of societies around the world. Rain refills our lakes and reservoirs, providing the water each of us needs every day. It feeds us by nourishing our soil, enabling our crops to grow and our livestock to flourish.
雨对人类的这个生存和发展是有非常重要的这个意义的。
But as rainfall patterns become more unpredictable, how will our relationship to rain be transformed in the years to come? And how do we make the most of this precious resource? Today, as we face unprecedented changes in our climate, our ability to forecast where and when rain will fall is becoming increasingly important. To aid us in our quest, we turn to satellites and supercomputers, to laptops, and even to pen and paper. And if all this fails and the rain does not fall where we need it, we turn to science.
It's been around us all this time. I mean, how big is the thing falling on your head in a thunderstorm is a question we still don't have great answers to.
So rain is not an exact science. But one thing that is becoming clear is that in order to survive the challenges ahead, we need to learn more about rain. When the Earth was first formed 4.6 billion years ago, it was hotter than the Sun is today. But following a cooling off period of 600 million years, the vapor that encircled the planet cooled and turned into rain. Then the Earth suffered a period of torrential rainfall that lasted almost 3 million years. This created the seas, lakes, and rivers of today, which covered 2/3 of the planet in water. But how do we know this? And in what way does this knowledge help us understand the world we live in today? We can find some of the answers by looking underground. Scientist Cormac O'Hamel is fascinated by the traces left on ancient rocks and fossils by prehistoric raindrops.
Well, he'll miss your real grachni the malakacha yet uvenum. Agus he'll mention agus shilam go fool. Gerbala commerce e uv. Eder mehen sni show agus na keen ishana. Ka star scriefe in zijn uv. A janga a granter na valley.
This landscape in County Fermanagh exists thanks to the abundant rainfall it enjoys. Yet beneath the bog lies a more alien landscape, the Marble Arch Caves, also shaped by dramatic downpours.
Is Jas on Gamor eventually a gark or Rhoda Crohi go father shin sheer. As Kajay Crohi na Hovana, Jora Begga Ishke, a hitch was her Hilka, Ogs a Hannick and Balashaw leg. Can I shop? Said the Reach Tool. Better than his far and I should be Alice na Hovana, a nurse in the Vekel. Shin eel Hishni, Hasten Shin. August Shitson. Tan kunshin hals o chornil har vermeider go lei herad. Maar taas ook hem. Go shillen. Iske een noos en shin. Iske a hitch maar eigen hoos en shin er een dromkla. A hanneke noos fried. An eelkloche ligget hals a chon. Agus a hanneke noos. Agus a dag calcite in a jee. Agus a good shiloshies gebon an eelchishne shin. Agus fagenche calcite. Eg raat a hartfe centimeter a wan. Gach mile blien. So that she shin meder go lei herad. So shin ked go lei mile blien o hussy and crohushin. Agus the ruddy ella Holland shin mar hamplet that kionna talan comor with better near smoke and shin ye reached. The ruddy ella foster and clock shin. Crohio shin hard for 3 million blien ahen. Agus ta the cannula have a gerstig an arm. Steens and Clockshin, the Jocolina Leo. That alles in Shin are an atmosphere of the onagus. The can you iron veins in an atmosphere, Shin August by your chas an atmosphere. No, there's a shock. Cruhio show, oh no crowerly than the min red by no min anvia bagger, there are any monococcus. August in the shits and bio, black shits and just in the crowerly. Finisher. Ar na cannula have on again am agus tan ine sé sin stís a charrig sin go fór. Gach neach bio ar an dóin seo tá isce onta. Gan isce ní betha ar bí on. Tá isce go táhaach sin, tá isce go specialta sin. Nuair bíon ólíthe géirí fisrú bhfuil bíon beochta bí sa chruinne. Bín siad a cuatú bhfuil isce on. Má tá isce on tá seans go bhfuil beochtán. Mona bhfuil isce on tá siad cinse nach mé beochtán.
Over 71% of the Earth's surface is covered by water. 326 million trillion gallons of it. But 97% of it is salty, and 2% is trapped in the poles. So all of mankind relies on just 1% to survive. But because much of this clean water lies underground, humans have mostly relied on rivers, lakes, and reservoirs. These are constantly refilled by the water cycle. As water evaporates into vapour, condenses into clouds, and falls back to Earth as rain. Despite rain being essential to our lives, it's something that we know surprisingly little about. Dr. Mike Larson is Associate Professor of Physics and Astronomy at the College of Charleston and specialises in the study of raindrops.
I study rain because it's an accessible part of the universe that I don't know that much about yet. The technical definition of a raindrop is something that falls out of the sky that's in liquid form that's at least 0.5 millimeter in diameter. The process of rain formation is a very complicated one. You have to start with a dry aerosol particle or a piece of dust or dirt in the air. Aerosol particles can be a variety of different sizes, but a medium-large aerosol particle might be in the neighborhood of 1 micrometer across. That micrometer across particle has to grow eventually to become something that's basically 1 millimeter across to be a typical raindrop.
So first things first, I'm going to write right up here because it's a common misconception that raindrops are not shaped like teardrops.
A raindrop shape is the result of a balance of forces. And the reason anything has the shape that it has is due to the fact that that's going to be the thing that minimizes the energy associated with the system as a whole. For most situations, the way you minimize an energy is you make something spherical. None of them are going to look like a teardrop. On average, you're either going to be spherical if you're small or wider than tall if you're large. The speed at which a raindrop falls depends on its size. The smallest raindrops fall slower than the larger raindrops, and so the smallest ones fall 1 to 2 meters per second, a few miles per hour. And the fastest raindrops are going to be falling in the neighborhood of 9 or 10, maybe 11 meters per second.
And the way Mike measures this is by using a device pioneered in the early 1990s. A distrometer can work out the speed and size of individual raindrops.
This is the #1 piece of equipment that we use to study rain variability. There's 2 lamps here, halogen lamps. The light bounces off this mirror, goes through a Fresnel lens, which widens the light beam, goes through this slit, this slit, this slit, and this slit, off that mirror into the camera. And you have a parallel path on the other side. Bounces off this mirror, goes through this lens, through these 4 slits, off that mirror, and into that camera. And those cameras are the ones that are taking 55,000 pictures per second. As rain falls through the center, it is seen by both cameras, and the view of one of the cameras is about 7 millimeters taller than the view of the other camera. This slit right here is vertically offset from this slit right here by a fraction of a centimeter. So that slight difference in heights where the 2 cameras are looking allows us to calculate the fall speed of the individual droplets, because we can figure out how long it takes to be seen in one camera compared to the other camera.
Back on campus, the data recorded on the distrometer helps Mike to interpret the radar measurements of actual storms.
We basically get this large list of information about each individual drop detected in the storm, telling us about, on average, do the drop sizes get larger as the storm progresses? Or is it more likely for the drop size distributions to be wider? If we explore and examine these drop size distributions in more detail, the hope is that we can determine a little bit more about the creation mechanisms in different storms, or potentially how to better outline the physical processes that go into going from a cloud to a full precipitation drop. And I find that fascinating, that it's been around us all this time. I mean, how big is the thing falling on your head in the thunderstorm is a question we still don't have great answers to. And I think I can help there.
If learning about raindrops helps us understand rain, knowing what happens when rain is scarce helps us understand our history. Professor Lian Cheng Tan has studied the effect of droughts on people living around the Dayu Caves in the Qingling Mountains of China.
雨对人类的这个生存和发展是有非常重要的这个意义的。像我们都知道，这个生命的发展它有3个要素，最重要的水、空气和食物。所以呢，水是排在第一位的。因此这个水不管是对于我们的这个植物也好、动物也好，还有这个人类也好，它都具有非常重要的这个作用。
The Qingling Mountains are an important geological boundary within China, separating the rice-growing regions to the south from the wheat-growing regions to the north.
所以研究秦岭这块地方的这个气候变化，对我们理解整个的这个我们国家的这个气候，还有包括为这些重大水利工程的未来的这个安全保障，都是有很重要的意义。
In 2015, Professor Tan visited the caves to study stalagmite formations, hoping to find patterns of climate change. But he discovered ancient inscriptions that contained a wealth of historical information which transformed our knowledge of the past.
这些字都比较敏感，后来一看到，就看到那个题词里面有记录天旱的这个字眼。后来我就特别敏感，看这个字之后就特别兴奋，就想着，哎， 这个是不是既然这个时段记录了天寒，那么过去的那些题词有没有在记录天寒的这种事件？
Analysing his samples, Professor Tan found the charcoal deposits on the stalagmites came from the torches used by people visiting the caves. When he dated these deposits, he was able to create a detailed history of the paleoclimate of the past 500 years.
所以我只要通过碳丝的测年，把这碳线的年代测出来，我就知道那时候什么时候这个有人进去过，再把这些人进去过的这个时间，再跟洞穴里面那些墨书题词的时间就可以对应起来。
He was then able to compare his findings with major historical events and work out how climate may have affected the course of history.
明朝嘉靖7年的这个干旱事件，他当时汉中世志就记载叫大饥，然后人相食。
During the 17th century, another decades-long drought caused widespread famine and led to multiple rebellions against the Ming dynasty.
那么中央这是一方面起义军的这个打击，另外一方面再加上关外满清的这种入侵，所以这最后最终导致了这个明朝的灭亡。这是我们从古气候的学的角度来讲，就是说气候的恶化对明朝的灭亡是产生了非常重要的这个影响。
In paleoclimatology, reconstructing ancient climates is an important way of understanding natural variation and also the evolution of our current climate.
然后再进一步来通过过去的变化，通过我们对过去变化的规律的这个探索，然后我们就可以通过建立一些模型来尝试性的来预测未来的气候变化。
But what caused the severe droughts recorded on the walls of the Dayu caves? China and other countries in South and Southeast Asia are dependent on the monsoon. Between May and September, a seasonal southwesterly wind blows in moisture from the Indian Ocean. Whilst the rain the monsoon brings can lead to devastating floods, they're essential for a country such as India, whose infrastructure and economy is dependent on this rainfall.
Most of our crop or agriculture activity are rain-fed, and therefore any failure in the monsoon in any of the year, there will have a cascading impact on various aspects of our life. People will start migrating from villages to cities, so the burden of the cities increases. Again, there also water shortage will come because of this population migration of that.
Tracking the movement of the monsoon weather system allows the country to prepare for different scenarios. That's why the Indian government set up the Monsoon Mission Research Centre in 2012.
Now this monsoon mission has provided us, very good forecasting system based on dynamical models that can give you prediction for several days to weeks to month to season. If the seasonal predictions are indicating that a drought is possible, what you can do is you can go for crops which are drought resistant. You can reduce the crop area, thereby use available water only to grow small amount of crops. Similarly, if you are expecting a lot of rain, dam water management can be done properly. You have to release the water, otherwise both rainfall and dam water can actually flood your cities or villages. And similarly, water supply for cities, etc., you can exactly plan and thereby reduce the wastage of the water.
Increasingly erratic global weather patterns are making the work of the monsoon mission even more important.
Extreme events like drought or heavy rainfall is going to be increased. These extreme events with the climate change is becoming more difficult to predict also.
Using the latest technology is one way of tracking our changing climate. But across the world, many amateur enthusiasts gather precious weather data using more conventional methods.
Man is really powerless against the forces of nature. There's an old Irish saying, we say, "Ní he lá na guithe lá na scolab," so what it means, we say, like lá na guithe, windy day, we say is not the day for thatching. What I'm close to here now, we say, is an automatic rain gauge. It's actually called a pluviometer because the French for rain is pluvo. So it works on about a weight system underneath it here, and also there's a laser system, and that detects, we say, if rainfall is falling at any stage. It's very, very sensitive. The least amount of rain that falls is detected. This is the first rain gauge that came in here to this enclosure back in 1984, made of copper. 5 inches diameter and 5 inches deep. And down into it then you have a bottle which decants or collects the rainfall. Now just taking a look here, like since 9 o'clock this morning, I'd say we've had about 5 millimetres of rain, with quite heavy rain there in the last hour, so I'd say about 5 millimetres of rain there. But I leave it back in here again because we're filming during the day, and I'll check it in the morning again, we say there at around 9 o'clock in the morning.
Once the data's collected, David records his findings using an intricate set of specialist symbols.
This system here now that I'm using is what's called synoptic code. It can be read by any meteorologist throughout the world. I just put in the time here, 0700. There was mist condition at that time, which is just two little small horizontal lines. There's about 300 different symbols in it. The type of cloud, the wind direction, the wind strength, prevailing weather at the time, or the past weather, is all included in a code.
This is more than just a hobby for David. At the end of each month, he sends his findings off to the professionals at the National Meteorological Service, Met Éireann. This observation station in County Kerry is one of 25 stations which monitor Ireland's weather. While the data recorded in these high-tech stations let meteorologists create up-to-the-minute weather maps, the work of David and like-minded volunteers is used in equally important ways.
Eibrecha dónacha agan agus didn't siad obair fear tábhachtach go Met Éireann. Is sais meteorolaí amateurach iad agus caitheann siad dar síl ar fad ag tóga leachtaní sna tíche agus ag dar chuid fermachaí in átaní iargúlta nach bhfuil stáisiúnaí amsir agan.
Bailíonn muid an tola se go léir agus chuirtear isteach I bunach ar sunraí agus tá siad ar fáil the gachtainna. So it tá picture umlán den tír agan leis na sunraí so agus úsáideann an rain éráide na figurí soch an trocht dhéanamh ar an athrú éráide an athrú san pátrún báisteach agus athrú na séasúr agus mar sinnda. So is féidir leo an báisteach anuú a gur gúmparáid leis an máisteach Trocha blian ó hin, chaige blian ó hin, so yeah, tá si fearthach doing.
We have recorded rainfall and weather data manually for centuries. But it wasn't until the 20th century that weather prediction developed in leaps and bounds.
The term atmosphere in about 1900 meant pretty much surface weather, maybe a little bit of mountain weather, and you were pretty much stuck to looking at the clouds from afar. In the middle of the 20th century, those radio balloons and some aircraft were able to go up into the middle atmosphere, and our whole understanding of atmospheric dynamics began to be revolutionized.
The resulting scientific advancements led to the launch of TIROS in 1960, the first ever weather satellite.
The television weather satellite started a trend that maybe we'll never have another surprise storm. We'll always be able to monitor the atmosphere. One of the reports at the time said, we wish to monitor everything atmospheric everywhere always. That was the phrase.
This development was given a rocket boost when President Kennedy announced that the USA would put a man on the moon. And from the start, weather forecasting was one area the space program was intended to benefit.
Fourth, an additional $75 million, of which $53 million is for the Weather Bureau, will help give us at the earliest possible time a satellite system for worldwide weather observation.
That first ever image of the Earth from space, sent back by Tyros, was a massive breakthrough. Suddenly, as well as the rotation of the Earth, we could follow large-scale weather fronts for the first time and track the movements of the Earth's atmosphere. By today, thousands of satellites orbit the Earth, many of which are used for weather and planet observation. At NASA's Goddard Space Flight Center near Washington, D.C., scientists have used these satellites in a groundbreaking project.
The Global Precipitation Measurement Mission is a mission that's co-led by NASA and the Japanese to look at rain and snow around the world. But it doesn't do this alone. We've launched a core observatory in 2014, but then we are able to work with other partners around the world in Europe, in Asia, South America, and the United States to look at a global picture of precipitation, both in our communities and around the world. It's pretty cool technology to be able to measure rain and snow from 250 miles up. And the way that we do that is we actually look in the microwave frequencies. We can observe those signals passively to tell whether a storm has light rain or heavy rain. And then we can also look at it more in detail to be able to tell the different types of particles, whether they're ice or snow. Understanding what's happening from space is vital. We're able to get a global picture of precipitation. And so that type of information is fundamental into numerical weather prediction or to understanding our weather models, giving those observation data points into the models to be able to better predict our weather in the days to come and even looking at our climate in the years to come and decades.
Data from the Global Precipitation Measurement Mission's fleet of satellites lets meteorologists around the world study the way large-scale weather patterns interact with local systems. Scott Duncan is a professional meteorologist from Scotland. His line of work demands he keep a constant eye on the latest weather around Europe. Today, he's on a hill outside Glasgow, comparing satellite images with what he himself can see.
Well, in Glasgow, le brúgar stekin stuur, le emischer gemacht soccer, savach blas, chirm. In Jelvin Satcho, hafisachum gevel skoin, dirk to Glasgow, agus well, hey, was green nach Glasgow, agus to le bicken cumulus, agus beauty to show feikin in Satcho, when I ket shees. Actually, le TVJs and stratus decan kuchak.
The weather information that satellites record are fed into supercomputers able to process huge amounts of data.
In Europe, I seen the hokol Jalvin satchel a hula quick minute. Ach, ons na station unichtje, han data chin stach a hula minute. Uwzach minute and data ursha. A supercomputers uwzach more as kuachach. I to jeliki kri barach sheskit quadrillion some gach jik, no sheskit petaflops, no petaflopichin. Leonig supercomputer talaspors le processors as hardware. Before gan a supercomputer shot ro gallion nesjar a chruchich huin.
All this computing power is one reason today's 4-day forecasts are as accurate as 1-day forecasts were 3 decades ago. The Burnsday storm of 1990 caused extensive damage and loss of life across Ireland, the UK and Northern Europe, despite being predicted.
Cratá tar uine ac in son Jessica's and Stormshire van Jalvin Satchel gema bunneteach agus va da bate a crunich data as a goeie sheer agus va eet oversach kutermach son a ravach ideenuf son a dunia on an alp agus in Yorpe.
Today, Scott is part of the international energy industry, providing forecasts for markets across Europe. But he's also a climate change communicator. His graphics and weather charts have been retweeted by the World Economic Forum and climate activist Greta Thunberg, among others. While Scotland might not suffer the more extreme effects of global climate change, Scott does believe these changes will affect the prevailing weather patterns here.
Han tuvenir tornes fluche na tuvenir. Ha seo skas mar ha go avistach a chain van tuvenir. Han Atlantic agus na beanten arst tuvenir a garstachig and je guske a tustium. Kutchach han a beanten tuvenir a tors faski don tuvenir van vorchuch den uske. She skal uske na rain shadow a hakin seo. Le blachig na crunne hasen dulgum fasen tuvenir nas fluche agus gum be tuvenir gumanis tirm. Lis gevel commis toish en chiche fasen share suringun ravige horst de tuenich is a fopon nas traie mun droch hiche. Ha sjo geharich kutermach der ha tachert se more emischer richien lech tirmich na tul uske.
To keep up with these changes in weather systems, our knowledge of how they are created needs to continue to develop as well. And an important element of this is knowing how clouds form. Professor Raymond Shaw of Michigan Tech has dedicated much of his career to studying clouds.
A cloud is a collection of droplets or ice crystals. So the ingredients of a cloud are water and something for that water to condense on. And we call those aerosols. These are small droplets or small particles that are floating around in the air. Without the aerosols, clouds simply wouldn't exist on the Earth. When we say cloud, we usually are referring to a whole collection of those particles. And that could be a fog close to the Earth. That's like an Earth-connected cloud. Or it could be, deep clouds over the tropics can extend from almost close to the surface up to the top of the atmosphere. It could be 10 kilometers deep. So there's a whole range of sizes and scales. And that's one of the things that makes the cloud problem, trying to understand the processes that are happening in clouds. Will they rain? How much sunlight will the cloud reflect away back into outer space? To answer those questions, we need to understand processes happening at all of those scales, from the scales of a single droplet, as small as that droplet is, all the way to the turbulence and the convection and eventually to the full scale of a cloud, a storm or whatever system is producing the clouds. How much water a cloud holds depends on the size of the cloud and most importantly, the depth of the cloud. Also the part of the Earth that the cloud is on. So if you take a cloud over the Arctic, the cloud almost doesn't exist. There's just not a lot of water vapor in the atmosphere in cold conditions. But in a warm place like in the tropics, the clouds can be really juicy. They can hold a lot of water and you can get, many, many centimeters of precipitation.
And in order to study these different types of clouds, Dr. Shaw's pioneering cloud chamber is an invaluable tool.
A cloud chamber is basically a container or a box that allows you to create your own environment. The cloud chamber itself is 3.14 cubic meters, and that's why we call it the pi chamber. It's the only convection chamber in the world. You can control the temperature, the humidity, and perhaps most importantly, you can control of the aerosols that you put in.
Okay, we're going to close it.
Rather than being like the referee that's watching the soccer game, you can actually be one of the players in the game, so to speak.
Yeah, we were trying to get some of them with a long enough exposure.
Things that we've been really focused on are how do aerosols and clouds interact with each other. But it turns out that clouds themselves influence the aerosol particles. So they basically can consume the aerosol particles. They can help remove them from the atmosphere. They can actually cause chemical reactions to happen. They can allow aerosol particles to change their shape. And we can look at those processes in great detail in the pie chamber. No single tool is going to solve the climate problem. It's not going to complete the whole puzzle by itself, but it's an important piece of answering these kinds of questions.
If aerosols are a vital part of cloud formation, what happens when too many are pumped into the atmosphere? They become pollutants, overwhelming the natural cycle, and that can lead to acid rain. As Dr. Eddie Graham, a lecturer at the University of the Highlands and Islands, explains in his online lessons.
Now, rainfall by its nature is naturally slightly acidic. It has a pH of about 5.5 or 5.6. That's due to carbon dioxide in the atmosphere. However, acid rain is when it's got an anthropogenic origin. That means it's created by humans, and it's due to pollution in the atmosphere. Hoshig on triblage ishka sharavakik, asje on Hyundai Gunivacus, Industrial Revolution, and on Neuvlin Jaeg. She chemiker Alabanak, Robert Angus Smith, a Kuran Anam Air ishka sharavakik. Fure mak guvel nor a loskuk shin guel le tor sulfur, shine an aver a han ishka sharavakik a chitum von Skohen. Just to give you an idea of how severe the acid rain problem was at one stage, in 1979 in West Virginia in America, a pH of 1.5 was measured at one weather station, one rain gauge. That's actually almost as strong as battery acid in your car, which is pretty concerning indeed. Places in the Far East today, which are industrializing very quickly, are seeing massive increases in problems related to acid rain. So acid rain hasn't gone away. We've just exported the problem to more eastern countries.
Though in the West, reducing fossil fuel use has brought acid rain under control, the content of rain is still closely monitored. At this bog near Edinburgh, Scotland's capital city, scientists monitor hundreds of different atmospheric components.
The focus at our site here is not measuring the rain quantity, but the quality of the rain, what's in it. And to also measure the air that goes with that rain, since the two are interacting. By measuring them simultaneously, we get a good understanding of where the air pollution is coming from and therefore what it's going to be doing to the ecosystems.
The site is a vast peat bog, one of Scotland's keystone ecosystems, one vulnerable to environmental degradation.
I think the main challenge now is that it's still full of what's called nitrogen pollution. That comes in two forms: nitrate from cars and fossil fuel burning, and ammonia from farming activities, from urine and dung emitting to the atmosphere. But what we're finding is that a site like this, it's not just the rain that's important, it's the rain in interaction. To give you an example, we're seeing that a more extreme situation from colder winters, hotter summers, affects the summertime emissions of carbon dioxide. So carbon dioxide, a greenhouse gas. A site like this hopefully would be absorbing carbon dioxide from the atmosphere. Peat is the carbon dioxide store. And with these changing winters, warmer summers, we're seeing this changing around to become a source. So the site is losing carbon dioxide to the atmosphere. It means climate change is encouraging more greenhouse gas emissions to encourage more climate change. We've come into a positive feedback.
Despite the global drive to reduce carbon emissions, Peat bogs such as these are good indicators of how our actions are having a direct impact upon the environment. 90 years ago, on the prairies of Canada and the US, poor farming and land management methods, combined with periods of severe drought, led to conditions known as the Dust Bowl. This, combined with previous disasters, made the Great Plains of America fertile ground for opportunistic rainmakers and charlatans who made money out of people's desperation for rain by peddling pseudoscience and fake spirituality.
Turns out that if you pray long enough, it'll rain. If you shoot fireworks up, it'll rain. If you're desperate, you'll try anything. And I think a lot of these people were desperate. Not all the people were trying to sell their wares, but the charlatans of the American Great Plains, they definitely were. And they were rainmakers and rain fakers ever since.
One of the earliest pseudoscientific methods was known as concussion, which claimed that loud noises could agitate clouds and so make it rain.
Concussion method was an outgrowth of pretty much the US Civil War. After the Battle of Gettysburg, there was a gigantic rainstorm. There was nothing special about that, but they did think that the cannon and the roar of battle and the smoke were causing a disruption in the heavens. So the government in 1890 did sponsor General Dryenforth to go out to Texas and to try to cause it to rain during a drought. He tried to make a kind of a Civil War scale battle, and the more he shot it off and he took credit for any nearby rainstorms, he tried to make a report that said, "I made it rain."
These experiments even passed for entertainment.
They had the townspeople turn out in droves. And so, I mean, what are you going to do in the middle of the summer in Midland, Texas in the 1890s? Go to a great big fireworks show. And it was very popular.
By the middle of the 20th century, the US military had taken an even closer interest in the possibilities of controlling the weather. This time, the methods had a more credible scientific basis.
Operation Popeye was an idea that we could use environmental warfare in the Vietnam conflict. They thought if we could make it rain over the Ho Chi Minh Trail, it would be harder for the infiltration to come down. They had an Air Force base in Thailand that was tasked with setting off these silver iodide flares over the Ho Chi Minh Trail. It was so secret that the head of the base didn't even know what they were doing. It became a great big front page newspaper story. It led to a UN resolution that was banning the hostile use of weather modification as an agent of war.
The technique was called cloud seeding and was first proposed in the 1940s, but for more benign reasons. Project Cirrus involved silver iodide, today more commonly known as dry ice, which was dropped into the eye of a hurricane to modify its power.
And so flying out of Florida, they flew into a hurricane. And they put some dry ice into it, thinking that it would reduce its destructiveness or drive it back out to sea. Well, when they did seed it, the hurricane stopped and went directly on shore and basically devastated Savannah, Georgia. It was completely unexpected.
Details of this hugely embarrassing mission were buried in a top-secret archive for 30 years. But recently, there have been several breakthroughs in the science of cloud seeding, and the United Arab Emirates is one country that's leading the way. At the National Centre of Meteorology in Abu Dhabi, the government runs a program that seeds the clouds above the desert.
Here in the UAE, we do not have natural water resources. We do not have rivers, for example. So we only have rain and desalination. And of course, we wanted to get the maximum out of each cloud in terms of water and rainfall. In arid and semi-arid region, we think this is one of the most important methods.
Although actual rainfall is scarce, clouds form above the UAE on over 200 days each year, and a large percentage of those clouds are suitable for cloud seeding.
Basically, the technology is that we use hygroscopic materials. This is the idea, is that you want to help in a microphysical process that happens inside the cloud, which is you want the droplets basically to hit each other in coalescence, so that the water droplet grows bigger and then it falls on the surface. And then we send our aircrafts to take these materials to the base of the cloud. So once we put these materials inside, then with the motion, the up motion of the wind, then it takes these materials inside the cloud, and then this process happens. So you have a bigger water droplet, and then it falls as rain. What happens is that sometimes you have a cloud and it has water content in it, and it starts raining, but the droplets are so tiny that they evaporate even before they reach the ground. So by doing the cloud seeding operation, we make sure that we have a bigger droplet, and then we make sure that we get the maximum out of each cloud. Our forecasters here, of course, they see the weather. They know that after 3 days, for example, we have a good situation of forming clouds, so our team becomes ready, and then we immediately dispatch the aircraft to do the operations.
Go to location 257. At 99.
We're on duty all the time in case there's weather coming. We get to 3 days advance notice, but then all of a sudden there's poof, something pops up and it's like scramble. We've got to go and get to this cloud that's just showing up. We're looking for towering clouds, the fluffy clouds that grow rather than the flat sheet clouds. There's an updraft within that cloud, and we're trying to penetrate into that updraft and release the salts in that location so that then they can be carried up into the cloud and mix with the water vapors and coalesce and form droplets and fall as rain. It can be quite exhilarating. There are some unusual experiences dealing with the clouds. When we do penetrate into that updraft, it's like the aircraft's becoming a glider. We're suddenly getting this big vacuum cleaner pulling air up above us. The aircraft is just gliding around at 300 kilometers an hour just in this updraft with no assistance other than the cloud pulling on us. When I fire the flare and I circle back around and come back through 2 minutes later and seeing the change, whether it worked or whether it didn't work, and seeing the result on the weather radar live on the aircraft and just seeing it, you know, just forming and falling as rain.
We see many countries now, either they started a long time ago in cloud seeding and now they are coming back. I think, especially here in UAE, I think the project is valid with the results that we've seen. It shows that, yes, we have to continue in this, and we have to continue advancing the science in this field.
Each year, as more and more communities find themselves living in areas of the world prone to drought, our ability to forecast the weather, and rainfall in particular, is becoming ever more vital. As our weather becomes increasingly erratic, with climate change often leading to either too much or too little rainfall, whether we like it or not, our relationship with rain is changing.